We're talking about our next unit, which is Chapter 5, Polynomial Functions and Equations. We first have to be able to identify polynomial functions, what they are. Why is that important, you ask? Much of the work that we do in Math 30 and in Calculus and in future math classes depends on our knowledge of polynomial functions and their relationships. So there's some language we need to get used to. We have coefficients. They're labeled ANs, so AN minus 1, all the way up to A0. They're usually numbers of some description. They might be radical signs. They might be fractions. Coefficients can be anything you want. The coefficient of the highest power of x is called the leading coefficient. So that's going to be the AN value. The term that doesn't have an x on it is called the A naught value, and that's referred to as the constant term. And the degree of the polynomial is the highest exponent we find. Our exponents must be whole numbers, 0 and larger, to qualify as polynomials. So in my first example, I've got a polynomial statement. All the exponents are whole numbers. The degree of the polynomial is 4. The leading coefficient is 1. That's actually not written there, but it's a 1. And the constant term is 5. So we're supposed to be able to look at polynomial statements and identify whether they're a polynomial function or not. Keys that things are not polynomial functions, fractional exponents. So that's bad. Exponents that are not positive, that's bad. So that's a no. Exponents that are not whole numbers, like this one is going to generate an exponent of 3 over 2. So that's also bad. This is bad because you can't take the square root of -3, so that's not a polynomial function. What remains actually are polynomial functions. It turns out that this square root on the 3x squared will generate a nice exponent, x to the 1, and that will be a polynomial. So we have to be able to identify those variables or those terms. The degree of example 3a is 3. It's actually hiding in the equation. So polynomial statements are usually written in descending order. And then it would be more clearly that the leading coefficient is -25 and the constant is -39. In example B, I actually don't have anything multiplied out. Now I could FOIL that. So foiling would lead me to numbers that I could understand. But the degree of the polynomial comes from taking the x's and finding the highest power of x I'm going to get. I'm going to get as the highest power 2. That's going to be x squared. My leading coefficient is going to be the number associated with that, which in this case is 10. And my constant is going to come from the numbers that don't have x in them when they're multiplied together. And that'll be the -1 and the +7. So I will have a constant that is -7. So we're going to apply that same type of analysis to equations that are a little bit longer. So the degree of the equation, I focus on where my x's are. My x's are here and here, my highest powers of x. So in the 3x minus 1 squared, I'm going to get an x squared. And I have another x squared hiding in that trinomial. So that's times by x squared. So I'm going to end up with an x to the 4. Which is the degree of my polynomial. My leading coefficient. My leading coefficient is going to come from that same multiplication step. The 3 squared, that's 9. 9 times 5 is 45, and 45 times 2 is going to be 90. So that was the 3 squared multiplied by 5, and then eventually multiplied by 2. Where does my constant come from? My constant comes from looking at the terms that don't have x's in them, the minus 1 and the plus 1. So the minus 1 will get squared. That's minus 1 times minus 1 is 1, times that 1 is 1. So that's minus 1 squared times by 1 and then times by 2. So my constant term that's going to come out of that one is a constant of 2. Try your luck at the next one. You'll notice that there's an addition sign in there. And that's going to change things a little bit. I'm going to a squared x in both terms, which is going to be my degree. My leading coefficient is going to require a little bit more work. The 3 is going to get squared, and then it's going to get hit with a 2. And then to that, I have to add 5. So 3 squared times 2, that's 9 times 2 is 18, plus 5 is equal to 23. Now my constant, got to follow what those non-x terms are doing. It's going to be negative 1 squared, hit with a 2. So that's 2 times 1. And then to that, I'm going to add 1, which is a constant of 3. Why would something like px to the or the function p evaluated at x be called a polynomial? It's called a polynomial because I can actually add the exponent of, or a power of x to the 0. And that x to the 0 actually doesn't change my value. It's called a constant because there is no change in the value. It doesn't matter what x is, the value will always be 7. Some more vocabulary. We can call polynomials by the number of terms they have. Monomial 1 term, binomial 2 terms, trinomial 3. Or by the degree. You can have a constant, which is degree 0. You can have degree 1, or degree 2, or degree 3, or degree 4. So degree 0 is called a constant. Degree is, maybe my room just has dead zones. Degree 2 is called a quadratic. Degree 3 is called a cubic. And degree 4 is called a quartic. There is language for 5 through 10, just like there's language for counting carbons in chemistry, 5 through 10, but we don't have to usually worry about those. You can also rate polynomial functions by the type of coefficients we have. So integral polynomial functions just have whole numbers, like the first example. Rational polynomial functions have fractions, so numbers that can be expressed as fractions. And real polynomial functions have expressions that cannot be expressed as fractions. Root 3 is a number that goes on and on and on forever, so I can't report that as a fractional equivalent. Turn the page over. We've got a few exercises to try with function notation. It gets us back into function notation. Go ahead and try these vocabulary terms out. You can check your answers in your answer book. If p at x is a given statement, but I know that p at 1 is equal to 9, I should be able to find the value of a. This defines for me that x is equal to 1 and p at 1, which I might call y, is equal to negative 9. So I might choose to write it like this. Negative 9 is equal to negative 3 times 1 squared plus a, which I don't know, times 1 plus 8. So negative 3 plus 1a plus 8 is equal to negative 9. That's negative 9 equals 5 plus a. And subtract the 5 over to the other side. I end up with a being equal to minus 14. Now I have two unknowns in class example 9. and two unknowns will require two equations. So I'm going to plug in the 2, I'm going to plug in the -3, and then see how beautiful the statements look. Remember, the context of the argument is my x value, and the answer is my y value. So my x value in the first case is 2, and it's equal to a y value of 18. So I'll work in red first. Negative 18 is equal to negative 2 times 2 squared plus a times 2 plus b. So that's a negative 18 equals 2 squared is 4 times 2 is negative 8 plus 2a plus b. Add 8 to both sides, that's negative 10 is equal to 2a plus b. I actually cannot figure out what either a or b until I look at my next substitution. And my next substitution says that x is equal to -3. So with an x value being equal to -3 and the y value being -13, I get to go -2 times -3 squared plus 8 times plus b. I think I found the dead spot, perhaps. I've kidnapped Mr. Wallace's sound system. So negative 3 squared is 9, and 9 times negative 2 is negative 18. I now have a -3a and a plus b. Add 18 to both sides. That gives me 5 is equal to negative 3a plus b. Now I have two equations and two unknowns. There's a variety of ways of solving them. I'm going to solve for the unknown by the method called elimination. I'm going to line up both equations over here. So negative 10 is equal to 2a plus b, and I'm going to subtract. The reason I choose to subtract is that b minus b is 0. I eliminate the b. Negative 3a minus 2a is minus 5a, and 5 minus -10 is equal to 15. So I can evaluate that a is equal to -3 by dividing by -5. And now I can go back and solve for b. I should be able to use either side. I'm going to go over to the other side and work in green. I now know that a is -3, so 2 times -3 plus b, that's negative 10 equals -6 plus b. Add 6 to both sides, so that's -4 is equal to b. I've been able to figure out what a and b is. This is one of the more challenging questions of this lesson, but there will be more to try. Thank you very much.